continuing to work with our probability distributions. We're just going to shift what we do with them a little bit. Today we're going to get a little bit more into our purpose behind working with probability in the first place. Why do we find the probability of things? Why do you want the probability of something happening? Why do you want to know it? It's a 40% chance of rain outside. Why do you care? Because it's the chance it's going to rain. Why do you care? Why do you care if it's going to rain? So you can be prepared, so you know what to expect. Probabilities is all about kind of knowing what is going to happen. That's why we do probability and statistics, is we're trying to take in information in order to make assumptions about what we think is going to happen. So, we find probabilities, but those probabilities don't tell us everything of what's going to happen. Especially as the number of things that could happen spreads out. Yesterday we dealt with situations where we were talking about flipping coins, or on your homework you dealt with ones that talked about rolling dice. The sum of two 6-sided dice rolled had a total of 11 different outcomes. You could get numbers between 2 and 12 when you roll 2 dice. Each of those different outcomes had a different probability. You could find which item had the highest probability, but it didn't necessarily exactly go with what you would expect. It kind of helped lead you in that direction of what you can expect. But today, we're going to get into talking about what is known as expected value. An expected value is a weighted average, also known as a weighted mean, of a random variable. Averages and means. They're a measure of center. They give us an idea of what we can expect to happen, but they don't always account for the fact that things have different likelihoods of happening. That's where, when working with probability distributions, we get a more accurate representation of what we can expect. Because of the fact that we can do a weighted average. We can do an average that gives more prominence to the things that have the higher probability of happening. The formula for expected value, which expected value is E of X. Again, not E times X, it is E of X. It is a function notation. Do not start multiplying E times X. It is equal to capital sigma. You clapping their presentations next door too? They probably did a wonderful job. So capital sigma, and then in brackets, X times P of X. Now the brackets are there to hold together what we're finding the sum of, because we talked about this a little bit back in chapter 10. Sigma notation, technically the stuff that goes into sigma notation should really be in parentheses. I did brackets so that it didn't mix up with the other parentheses in the problem. I could have done parentheses. Brackets like this are just parentheses, but they're meant for going around larger items. But sigma, the stuff that goes into it should be in parentheses so that it's all getting put into the sum. Now, breaking this down. Capital sigma tells me to find the sum, so I'm going to be adding a bunch of things together. Since it does not clarify where to start and where to end, the assumption is that you add all of it. Every single piece available to you. With probability distributions, we always work with every single piece. X has been our random variable. Specifically, it's the outcomes to what can happen. What's P of X again? The probability of the outcome X specifically. Okay, so break down this formula. What does it tell us to do? Add together every situation where you are multiplying an outcome times its probability. That's what it goes through and does. We do outcomes times probability, and we add it to outcome times probability, and we add it to outcome times probability until we run out of outcomes. So we can ask questions like, how many heads can you expect to be flipped when you're flipping 3 coins? If I want to do this, I need to know what all of my possible outcomes are and what all of their possible probabilities are. Aren't all outcomes and all of their probabilities built into like some fancy table that we made quite a few times yesterday? Called a relative frequency table? In fact, we made the relative frequency table for this setup yesterday. What were the different options for the number of heads I could get when flipping 3 coins? 0, 1, 2, and 3. What was the probability that we flipped 0 heads? What is that a probability? There was one way. Out of how many ways? 1/8. 1 out of 8. Probability of flipping 0 heads was 1/8. How about flipping 1 heads? 3/8. 2 heads? 3/8. 3 heads? 1/8. What should all those probabilities add up to? 1 or 100%. If they don't, that means we've missed something. Do they add up to 1? Sweet. Okay, so I need this information to find the expected value. But expected value is a simple calculation. Again, the sum of an outcome times its probability plus an outcome times its probability plus an outcome times its probability. My first outcome that I have written down is 0. Its probability is 1/8. I multiply them together. And then I move on to the next one. Add. Next outcome times was 1. Multiply it by its probability. I add and move on to the next one. 2 times 3/8. plus 3 times 1/8. That is extremely calculator friendly. You just have to type it into the calculator at this point. What is culinary making today? Ziti? I'm just smelling all the onions and it's just making me hungry. It smells amazing. Good thing it's only 8:45 in the morning. Now I want pasta. So I see that a number of you are doing this in your head. It's a doable problem. Don't get me wrong. But I have a feeling if I call on those people that they're not going to be able to give me an answer. What do we get? 3/2, aka 1.5. I don't care which way you give me the answer. Either is correct. Say for one thing, do you recognize that this is a word problem? Is it a word problem? Yes. So, E of x equals 1.5 is not a great answer to a word problem, especially when the word problem is how many heads will you get? Someone came up to you and said, I'm flipping a coin 3 times. How many do you expect that are going to be heads? And you answer them 1.5 of them. They're going to give you a weird look. Like, what are you expecting to happen? A heads, a tails, and then it to land on its side? To get the half? So, generally speaking, if you were to tell me E of x equals 1.5, I'm not going to be upset about that. You did the math correctly. But keep in mind that with a word problem, you also might want to answer like between 1 and 2. If it was closer to one or the other, I'd say about, and whichever one it's closer to, but this is a word problem. No, you are not going to flip a coin and get 1.5 heads. But it's also technically correct to have this. Now, that problem, many of you probably could have looked at it and been like, I didn't have to really do any complex math to probably guess that amount. And that has to do with what type of distribution that flipping coins is like this and the probability of getting heads and tails being the exact same. It gets a little more complicated with more complex distributions. Find the expected sum when rolling 2 6-sided dice. I need all of the outcomes. I need all of their probabilities. I already talked about the outcomes. The outcomes were between 2 and 12. What were their probabilities? Maybe having a chart would be helpful. That way we got something to reference. If only we'd done all these calculations. Oh wait, if you did your homework, you did. Well, why'd you go and do that? Yeah, I don't typically reference the previous day's homework on the current day's notes. For example, I don't typically, give you answers if you didn't do yesterday's homework yet in the middle of notes. How many different ways could we roll a 2? A sum of 2? One way, right? 1 and 1. How many different outcomes when rolling 2 6-sided dice? 36, because the first die has 6, the second die has 6, and 6 times 6 is 36. So this was 1 out of 36. Number of ways we could roll the 3, there were 2 of them. 2 out of 36 simplifies, though, to 1 out of 18. There were 3 ways to roll a sum of 4. 1 and 3, 3 and 1, 2 and 2. 3 out of 36 simplifies to 112. 4 ways to roll a 5, 4 out of 36. 19. 5 ways to roll a 6, 5 out of 36, doesn't simplify. There were 6 ways to roll a 7. 6 out of 36, 1/6. And then it started going back down in the number of ways. Rolling 2 6-sided dice is a symmetric distribution. This isn't what it asked for. This was just information that we need in order to find the expected value. Did you have to write it out? No, if you had it elsewhere, you didn't technically have to. But it's nice to know where the numbers came from if you're looking back at your notes. That's why I write it out. I want E of X. How do I find it? There's that many outcomes. Yes, you do all of them. What do you do with them? Multiply, add them together. That's very descriptive. You're right. There is multiply, there is add. What am I multiplying? Sum times its probability. 2 times 136. And then I'm adding the next outcome times its probability. And then I'm adding the next outcome times its probability. And then I'm adding, etc. Yes, there's a lot of outcomes here. It's a good thing this is calculator friendly, unless you really want to do it all in your head. You're welcome to if you wish. It's doable. It's not fun, but it's doable. 3 names? Let's go with 3 names. See if we can get 3 people with the same answer. There's the first name. There's the second name. There's the third. Scare you into typing things into your calculator is the goal.
I hope you call me.
Notice there's no calculators. My perfect.
I got notes.
Oh,
That's
not
that's
sure.
Julia, help me out here.
I'm still typing on it. Vivian, I got you.
John, what'd you get? Caleb, what'd you get? Keep going. Izzy, what'd you get? We got a 7. We got a 7. That seems like an odd number to go up to 7, doesn't it? Did you get 7? Sweet. It is 7. When you roll 2 6-sided dice, you can expect a sum of 7. Are you always going to get a sum of 7? Absolutely not. But it is the most commonly occurring one. The symmetry helps to bring that in with this one. So, expected value is going to have a number of different applications. It's going to have ones like ones we've did, and then sometimes it might sway a little bit and look a little different.
Wait, do we have to like do that formula? Because the first one, it was just like 1 and 2, and those were in the middle, and 7 was in the middle.
That's because of the symmetry. Has to do with the symmetry on those two as to why it went to the middle. It will not always do that. But why do we do this? Generally, it's not to look at dice and to look at coins. It's to look at things that maybe, like, I don't know, will cost or save you money. Say you purchase a raffle ticket. It costs you $10. There are 6,000 tickets sold. You want to figure out if you can expect a profit. So they advertise that the prizes are thus. There are 5,000 $1 prizes. I know, not great. But hey, there's a prize. There are 100 people who just straight up win their money back. 25 people win $100. Now we're making money. There are 5 people who win $1,000. One person makes $5 grand, and another singular person wins the grand prize, $25,000. So the question is it worth buying a raffle ticket? Is it worth the chance at $25,000? So, how do you figure this out? You go through and you find some expected values. In order to find expected values, I need every single possible outcome and its probability. Do I have all my possible outcomes? I see some people saying yes, I see some people saying no. Okay, we are trying to find expected profit. First off, are these profits? No, these are not profits, these are prizes. Profit implies it's what you made after you take out the costs. Those are not profits. So, I have to deal with that first. Since I'm looking for expected profit, my random variable X is profit. I won $1, my profit is -9. I won $10, my profit is 0. I won $100, my profit is 90. 1,000, 990, 5,000, I'd win 4,990 as a profit, and if I win 25,000, my profit is 24,990 because I spent $10 on the ticket. I need the probabilities of each of these outcomes. How do I find the probability of winning $1? How many ways can I win $1? 5,000. How many total ways can you have a raffle ticket? In other words, how many are there total? 6,000. 5,000 out of 6,000. You didn't know this, the simplified fraction is 5/6. Just for the sake of our notes, I meant to write this first. That way if people aren't here and they look back on it, they see where that came from. You don't have to write that. Okay, $10 prize, 100 out of 6,000. 1 out of 60. $25 out of 6,000. 1 out of 240. Again, I'm just writing where these came from on the side. You don't have to. If you are someone who's like, I won't remember, go for it. And I'm doing fractions because of the fact that I don't want these to be rounded. Because that'll throw off my answers. Okay. So I've got this. Now I go back to my statement from earlier. In order to do expected value, I need all possible outcomes and all of their probabilities. Do I have all of my possible outcomes now? No. What am I missing? Is every single ticket a winner? The number of tickets does not add up to 6,000, which means some people just straight up lose. If you did not win a single cent, what's your profit? -10. How many people straight up lost? 868. 6,000 minus all of these leaves me with 868 people that did not make a single cent. As a simplified fraction, 868 divided by 6,000 is 217 divided by 1,500. Again, for the sake of notes, for the sake of people looking back on it, I'm going to write where that number came from. So, big thing, you got to make sure you got all of the outcomes, all of their probabilities, and you also want to make sure you're paying attention to what it asked for. It did not ask for the expected value of the ticket. It asked for the expected value of the ticket. The numbers for my outcomes, for my X, that I'd be looking at were 1, 10, 100, 1,000, 5,000, 25,000, and 0 for those who didn't win. But since it was expected profit, I had to find the profit first, and then go through and do this. But then it's just outcome times probability, outcome times probability, outcome times probability, outcome times probability, and add those all up. And I'm just going to use parentheses to kind of hold my fractions together a little bit better on this one. I don't need parentheses. I can just use the time symbol. I've done the calculation already. It's -275. $2.75. Okay. What's your expected profit? -$2.75. In other words, we would expect to lose $2.75. Now, that can influence your decision to buy said raffle ticket or not. Now, there's more complex decision making that goes into it. You could talk about the maximum you can lose. You could talk about a lot of different things. I'm not trying to encourage you to gamble. Please make good choices. But I will tell you, generally, gambling, it's called gambling for a reason. You can expect to lose money. If you don't expect to lose money, you're doing it wrong. But expected value can help you make decisions not only on things like gambling, but it can be on things that are technically other things that you can deal with. Expected value is another thing that can go into helping you make a decision upon retirement. I know, you're a long way from retirement. So am I. I've got like another 90 years of working, but that's not the point. Eventually, you got to invest money and make decisions about it. So, knowing what to expect is an important piece, but is knowing what to expect enough? is a measure of center enough to make informed decisions? No, because you need to know what to expect, and you also need to know what other piece of information. What to expect, and how far it can vary from that expectation. How likely it is to vary from that expectation. A measure of center is the expectation. You also are going to want a measure of, what's the other one? Spread. Measures of center and measures of spread. The main measure of spread that we use with probability is standard deviation. Doing a probability distribution. Standard deviation is given by the lowercase sigma. It's given by said variable because of the fact that in probability you deal with all outcomes. Therefore, it's essentially working with the population. The formula goes as such. The square root of Yes, note the size of that square root that I just drew. It's a little obnoxious. It's meant to be that way. Don't worry, I'll give you something that makes it look a little less scary, I promise. I promise. The formula looks ugly. So did the formula for binomial distribution, but was binomial distribution in the end all that bad? We worked with patterns. Okay, some of y'all are like, yes, binomial distribution. The worst thing ever? Okay. Most of y'all, not so much. Okay. The square root of capital sigma. So the sum of, and we got a bracket. Inside that bracket, the first thing you'll find is a parenthesis. That's why we use brackets. So to differentiate between the bracket and the parenthesis. X minus e of x. Close the parenthesis, and don't forget to close the e of x, squared, times p of x. I know, it's a gorgeous formula, right? And by gorgeous, I mean really, really, really ugly. Okay, can you use the formula? Absolutely. It's easier to use a table. Not bad. Good eyes. Generally speaking, easiest way to do the standard deviation is to use a table. Technically, it's an augmented relative frequency table. Augmented means I've added things to it. So it's a relative frequency table that I've added things to. A relative frequency table starts off with your random variable, and then it goes into p of x. Here's the augmentation. We are going to add 3 columns. The first column says to take x and subtract e of x. Again, e of x, not e times x, e of x, and e of x represents what again? Expected value. The next one has a parenthesis and says to do x minus e of x in parentheses squared. Do you recognize that the only difference between the third and the fourth column is that the fourth column is squared? In other words, this entire thing says to take the previous column squared. Whatever number was there, you square it. That's what goes there. And if it's something squared, what do you know about those numbers? What are they always?
Positive.
They're always positive. The most common thing that I see people do is they don't get a positive number and put it in that row. Okay, the last row. X minus e of x in parentheses squared times p of x. This is the previous column again. And you're multiplying it times p of x. All of this takes care of all the things inside here. But there's a sigma that tells us, what do I need to do with all of those things then? Add them all up. So I also then need to find the sum of that final column. That'll take care of the sigma. And then I also need to then square root it. The sum technically is the variance, sigma squared. The square root of said sum is sigma, is the standard deviation. Standard deviation is a fantastic piece of information if your goal is to compare two things. One of the things you're going to see on your homework today is it's going to talk about an investment fund. It's going to give you probabilities of different things that you can get out of that investment. And you find the expected value and you find the standard deviation. From there, you make a decision upon which investment feels like the better option. Oftentimes, there's not a wrong answer. It's just a matter of what you're comfortable with. Because sometimes one investment will have a higher expected value, but it will also have a higher standard deviation, meaning you can expect more, but there's more risk to it. Are you a risk taker? Well, the other one will have a lower expected value, but a lower standard deviation often goes with it. Meaning, you can expect less, but there's less risk to it. And the key thing you have to keep in mind is when it comes to the standard deviation with probability distributions is you can expect, or it's common that the standard deviation, a very common probability piece is double the standard deviation is the amount that is not uncommon to differ from that mean. So, to finish off our notes today, we're going to find the standard deviation for above. If I ask you to find the standard deviation, again, you're going to want to make that table. X for the raffle was profit, and then we had P of X, and it goes X minus E of X, X minus E of X getting squared, and then X minus E of X getting squared times P of X. With the exception of the first two columns, you are better off when doing standard deviation to work from left to right. The first two columns, You fill in whatever way makes the most sense to you. Our profits were negative 9, 0, 90, 990, 4,990, 24,990, and negative 10. Their corresponding probabilities were 5/6, 1/60th, 1/240th, 1/1200th, 1/6000th, 1/6000th, and 217/1500th. Beyond those first two, again, you're better off working from left to right. My first column says to take x minus e of x. E of x for this problem was negative $2.75. Negative 9 minus negative 2.75. Be careful of your negatives. Negative 6.25. And here is why I work from left to right. After I've done that first calculation, the other ones are all built off of one another. So if I want to fill in this one, with that still on screen, I'm just going to click squared. And it's going to do the math for me. I don't have to type in a huge amount more. My last column was this number I currently have on screen still, multiplied by its probability. I generally keep at least 4 decimal places through this process. Zero minus negative 2.75. 2.75 squared. Oops. I accidentally clicked that twice. 7.5625. And multiply that by its probability, which is 1 over 60. The probability is the second list. 0.1260. If you know your calculator really well, there actually is a way of doing it in your calculator. It requires knowing a lot of things that we haven't talked about, and it takes much longer if you don't know how to do it on your calculator already. So. N. 9275. 8602.5625. 35.8440. I'm just going quick through and getting all these down. 992.75. 9855552.5625. 821.2938. Oops, one too many. I've never done the standard deviation with this data before. In hindsight, it's bigger than the one that I did. It saved us maybe a little bit of time, but not much. big number. And the last one's much easier because it's a smaller number. Okay, I know. Filling in this table can be tedious. I will tell you right now that most of the time there's not going to be that many outcomes. It's going to be a smaller version of this table. This one's just a little much. I tried to save us time by not doing my final example. Essentially was what I was doing. Okay, what do I do to finish this off though? The sum of that final column sum of that last column is this. Now, it might be off by a tiny little bit because of the fact that my calculator didn't round it when I made it do it. What do I do with that sum? Square root it. In that raffle, while you can expect to lose $2.75, don't be shocked if it varies by $330 or even double $330. It's things to keep in mind when trying to do anything that requires you investing money.
Is there a way to like write the answer?
That is the answer.
So we just put
Most of the time, if you fill in that last piece of the table, I'm good with that. Yes. Yes.